everybody, okay. Welcome to yet another revision stream. Yesterday, all we did really was look at the overall topic of the kidneys. We then covered the Krebs cycle and the Calvin cycle, just because I completely forgot how they worked, to be completely honest. But I'm hoping now that we've done that, it's a little bit more well remembered in my brain. So what I want to do is I think I'll quickly go over the Krebs and the Calvin cycle again, just to see what I can remember. And then from there, I have a past paper with a load of unique questions. Because I don't think this is actually a proper past paper. I think this is like a custom past paper. There are some challenging questions in this, and this is only paper 1 content. So I think we should do this on stream to see what I can kind of remember. So, there's a pen in the folder for some reason. So, let's go rub off everything on the board. We'll start with the Calvin cycle, because that links incredibly heavily to the light-dependent reaction. And as mentioned last time, the light-dependent reaction, the end product of the LDR is CO2, which, by just looking up the molecular structure of it, is 1 carbon. It's a 1 carbon compound. So, our CO2 goes into the cycle as a 1 carbon compound. It then combines with RuBP, which is a 5 carbon compound. So together, they become a 6 carbon compound, but this is catalyzed by rubisco, which is an enzyme. So rubisco catalyzes the reaction between CO2 and RuBP. We get a 6 carbon compound, but according to a lot of the mark schemes, I don't really think you need to refer to that. I think all you can really say is that you then end up with GP, 2GP, which is a 3 carbon compound. From there, these are reduced by NADPH, reduced NADPH, which gives you triose phosphate. And from there, 5 carbon is obviously going to go right back as RuBP, but 1 carbon is going to be used to assemble a pentose sugar. So, that is the Calvin cycle, basically. So CO2 combines with RuBP, catalyzed by rubisco, you get 2GP, it is then reduced by NADPH into 2TP. Then 5 carbon is recycled into RuBP. 1 carbon is used to create a pentose sugar. And therefore, it's a self-sufficient cycle as long as there is a supply of CO2 from the LDR reaction, which obviously uses water, I believe, because it's photolysis, I think. So, we'll quickly go over Krebs, which I probably don't even need to draw, I can just do it like this. Krebs cycle, we start with acetyl coenzyme A, which is a 2 carbon compound, and a 4 carbon compound. Together, this becomes citrate, a 6 carbon compound. We then get decarboxylation of citrate into a 5 carbon compound, reduction of NAD into NADH. We get decarboxylation of the 5 carbon compound into a 4 carbon compound, NAD into NADH, and ADP and PI into ATP, or basically just a gain of ATP. And finally, NAD to NADH, FAD into FADH. Obviously, then you can easily yap about this in relation to oxidative phosphorylation, where the hydrogen is donated to the electron transport chain. It travels down, releasing energy. This energy causes H plus ions to move, to diffuse through the cell membrane of the mitochondria, of the mitochondrial matrix membrane. From there, this creates an electrochemical gradient, so they travel back down via a channel protein ATP synthase, combining ADP and PI, and then O2 acts as the terminal acceptor for the end of the electron transport chain, which allows the electrons to be accepted, creating waste product of H2O, which has been released. And yeah, there you go. So, we're all thoroughly caught up. Let's go answer some of these questions. The first one: formation of an enzyme-substrate complex increases the rate of reaction. Explain how. And this is 2 marks. So we're going to want to look at, for 2 marks, either 3 points or 2 big points. The first point I said is that the substrate is going to bind to the active site of the enzyme, forming an ES complex. Then I said it reduces the activation energy by bending bonds. Now, I feel like this would be worth 2 marks, I think. I think I've hit everything. Reduces activation energy, and it says increases the rate of reaction, so we need to specify for the reaction to occur. And I think that should be it. Because I've mentioned substrate, I've mentioned the active site, which is you need to mention active site. If you're talking about enzymes, mention active site. If you're talking about enzymes, antibodies, or receptors, mention complex. You know, whether it's an antibody-antigen complex, a receptor, an adrenaline receptor complex. I don't care what it is, mention complex. It does reduce the activation energy, and it does so by bending the bonds. So I think that would be a very good 2 marks. I would love a question like that in an exam. I'm going to need a calculator for this next one. Okay. Scientists measured the rate of removal of amino acids from a polypeptide with and without an enzyme. With the enzyme present, 578 amino acids were released per second. Without the enzyme, 3 times 10 to the power of minus 9. Calculate how many times the rate of reaction is greater, give it in standard form. Okay, this shouldn't be too bad. Is this not literally just going to be plugging it into the calculator? We're going to do 578 and 3 times 10 to the power of minus 9. And that's probably going to give us a number in the billions or something like that. So let's have a look, shall we? 3 times 10 to the power of minus 9 divided by 578. That gives us... Oh, have I done it the wrong way? Maybe I have. 578 divided by 3 times 10 to the power of minus 9. Yes, we get 1.926 recurring times 10 to the power of 11. Or we could realistically just round this to that. So it is approximately, I mean, what's 11 figures? That's going to be well past a billion. That is insane. So it goes to show how vital enzymes are for metabolic function and why you die. You know, because if your enzymes get denatured, you're fucked. You're producing like a trillionth of a amino acid per second. So, we are going to show our calculation here being 578 divided by 3 times 10 to the power of minus 9. That gives us 1.93 times 10 to the power of 11. I think that is probably correct. Let's have a look. Okay. Another scientist investigated an enzyme that catalyzes the following reaction: ATP to ADP plus PI. Let's quickly do a little bit of a side talk about adenosine triphosphate, because I love ATP. It is one of my favorite biological molecules. We have our ribose sugar. We have our It is a ribose sugar, right? Because the structure of ATP and... I'll just say ribose. It obviously has the nitrogenous base, which in this case is adenine. And then it finally has... I forget how you draw this structure. It obviously has inorganic phosphates. We could quickly talk about the features of ATP. That's a very common exam question. And I always get it wrong, even though I know the answers to it, because I tend to overthink this one. One idea is that it's the immediate release of energy. One is that it can be rapidly resynthesized. One idea is that not all of the energy is released at once, which basically allows you to not kill the cell, because if you release all of this energy at once, it's going to cause thermal death of the cell. Not all the energy is released at once. So yeah, what are you gonna... I don't know where I'm gonna put it. I might keep him served somewhere. But yes, I will pay you for that, don't you worry. The scientists set up 2 experiments, C and L. Experiment C used the enzyme, so that will be ATP hydrolase? ATPase, let's just say. So, different concentrations of ATP and a sugar called lysose. So L has a higher rate of reaction, and the only feature that is different is a sugar called lysose. So lysose binds to the enzyme. Suggest a reason for the difference in results with and without lysose. So with lysose, there is a way higher rate of reaction. So what is going to cause that? What is going to cause a higher rate of reaction? Suggest a reason for the difference in results. I'm honestly not sure. Okay, I can make a logical assumption. Let's say that this is the enzyme, ATPase. Let's say that this is ATP. The idea is that lysose is going to bind Lysose is going to bind to the enzyme. There's a couple of alternative answers here that I feel. One could be that it just makes the enzyme overall bend the bonds faster, reducing the activation energy faster. One is that it changes the shape of this molecule slightly so that it's more easily able to bind with ATP. I don't know. I literally can't think of this one. There is a math question, but we could probably do though. Let's try this one. It says, calculate the rate of reaction of the enzyme with no lysose, so experiment C at 2.5 millimoles decimeter to the power of -3 as a percentage of the max rate shown with L. Okay, we can try this. So the max rate of L is 1.4, and it's asking us for 2.5, which is 6. This is going up in fuzz. So 0.44. So is this 0.44 divided by 1.4, maybe? It's a 1 mark question. So 0.44 divided by 1.4. Oh, fuck off. This calculator is so stupid. That gives us 31.4%. That sounds right. Lysose binds to the enzyme. Okay, I'm just going to make a logical assumption here. Let's say that lysose binds to just going to put a question mark so the teacher knows I have no idea what I'm writing about. Causes shift in the tertiary structure of the enzyme, making it more easily bind with ATP, so faster hydrolysis of ATP I have no idea. I'm completely improving that question. I would get no marks in an exam for that. Draw the general structure of an amino acid. Oh, okay, I might have this one in my bag. I might be able to draw an amino acid structure. Let's think about this first. Carbon, functional R group. Amylin group, which is NH, maybe? Hydrogen, helium, lithium, beryllium, boron, carbon. What group is nitrogen? Is nitrogen a group 2? Is nitrogen a group 2 element? Hydrogen, helium, lithium, beryllium, boron, carbon. Nitrogen's a group 6 element. One bond? There's going to need to be a double bond here, surely. 1, 2, 3. Oh no, I don't remember. Oh, I don't remember the structure of an amino acid. Fuck. I know there's a double bond somewhere. Carboxyl group is gonna need to be CO. Okay, let's think. Variable R group. Carbon in the middle. Variable R group. Carbon there. Nitrogen here. Hydrogen, hydrogen. OH. H. Double bond there. No. Wouldn't there be another oxygen though? Because it's COOH. Oh my god, why the fuck don't I remember this? This is like year 12 shit that we learned like right at the start. Why the hell don't I remember? Oh, well that's probably why. COOH. It is a COOH. So is it oxygen? Oh, let's see. I got it right. I got the structure right. Oh, thank fuck. Okay. So, that is literally the structure. Nitrogen isn't a group 6, is it? What element is nitrogen? Hold on. Is it a group 3? It is a group 7. So where's it getting? I don't do chemistry. I do not do chemistry. I have no idea why nitrogen is acting that way, but okay. We got it right. We got it right. I'm happy. I'm happy with that. Whew. Jesus Christ. For 1 mark as well, I would have been sweating that question so badly. Okay. Table 1 shows mRNA codons and the amino acids, so this is a codon chart, okay. The genetic code is described as degenerate. Use an example from table 1 to illustrate. Okay, this is a nice question. Degenerate. The idea there is that multiple base sequences code for the same amino acid. So for example, let's look at the chart. If we had UCC and a mutation occurred which replaced the C with an A, I think we would still get it. UC. Yeah. So if we had UCA and the A was substituted for UCU, no matter what, it would still give SER amino acid. That's the whole gimmick, is that DNA is degenerative. So, Probably could have worded that more scientifically, but I said multiple base sequences code for the same amino acid, i.e. UCA codes for so amino acid. If A is replaced with a U, UCU, it still codes for so. A scientist investigated changes in amino acid sequence of a human enzyme resulting from mutations. All these amino acid changes result from single base substitution mutations. This enzyme is a polypeptide 465 long. Okay. What is the minimum number of bases in this gene coding for this? What? Hold on. What is the minimum number of bases in the gene coding for this polypeptide? What the fuck does that mean? What are the minimum number of bases? Minimum number. Would that be 265 divided by... Sorry, 465 divided by 3? 155? That is such a horribly worded question. What the hell? Use information from table 1 to tick one box that shows a single base substitution but will result in a change from val to alla. Okay. Where's val? So that's G-U-U. It needs to be, the middle one is C. Which would be that one or that one. And it needs to start with a G, which is that one. Nice. Oh, come on. A change from glue to lyse at amino acid 300 had no effect on the rate of reaction. The same change at amino acid significantly reduced the reaction. Suggest the reasons for the differences between the effect of the two changes. So, we need to figure out firstly, what mutation type is it? Is it a substitution? Substitution mutation. Changes of amino acids. Changes base sequence. Okay, this is what I put. Substitution mutation changes base sequence. Amino acid 300 remains unaffected as DNA is degenerative. Amino acid 279 is different due to the changed base sequence. I should probably put coding for different amino acid. Different polypeptide structure, so active site for enzyme is less effective. Probably not going to get 3 marks for that, but I like to hope I ticked a few boxes. This is such a bulky paper. Jesus Christ. Look at how much more of this we have to do. Let me check. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 pages left. Oh my god, okay. I probably will stop at some point and do this, but hold on. Figure 1 shows a faulty form of meiosis that can occur in some plants. So the chromosome content of the diploid parent cell. So you get 2 daughter cells that don't develop. So instead of resulting in 4 unique cells, you're only getting 2 unique cells. And the chromosome content appears to be diploid, not haploid. So, complete figure 2 to show what the chromosome content would look like. Oh, bro, I fucking hate meiosis so much. This is one topic that I hate eternally. I hate this topic with a flaming passion, and I never want to do this again in my life so badly. I guess we'll draw 2 shots. I guess something like that. Something like that. To be fair, I'm probably gonna wrap it up here. Yeah, I'm probably gonna wrap it up here. What? How much have we done? Because I feel like we didn't do much there, but we definitely did. There is one more question, but that was a 2-mark question. There's one more question, and it says 3 of the bee species in the farmland areas were Pepernius prunosea, what does it suggest about the evolutionary relationships? What is, it's the genus and the species, right? The genus and the species, yeah. I don't know what else to gather from my question. It gives the name of three species. Two of them seem to be closely related because they have the same genus. One of them doesn't seem to be related at all. What can you draw from the evolutionary relationships? I don't know. Alright, well, I'll wrap things up here. Thank you guys for watching.